Appendix 1. Personalizing the workspace. Users can customize the assistant windows in the workspace. For instance, it is particularly useful to unpin windows when using the Analyzer and Compare tools so they can be viewed in the full screen. Hide the chooser by unpinning it. And observe that the tabs for the variables, components, and functions are then shown to the side. If you hover over one of the tabs, then it temporarily returns to its original position, but it will remain unpinned. If you want the chooser to be shown permanently, then it must be pinned back. Some users prefer the central window to take up the whole screen. To do this, unpin the Workspace Explorer, the Properties panel, and the chooser. When writing a formula, hover over the Variables tab to temporarily bring up the list of variables to use in the formula box. You can also click the Close button. To display the component again in its previous position, go to the View tab in the ribbon and select the relevant assistant to open it back. Appendix 2. Analyzer. To use the Analyzer, you need a results workspace executed in Sample All or Filtered Sample mode. When using the Analyzer, it is better to use the full screen to see the components clearer. Unpin the Workspace Explorer, the Properties panel, and the chooser. Go to the Analyzer tab. Press the button Confirm Layer Selection to move from the values in the data layer to the projection results. In the current location box, two elements will be available: Company and Realistic Layer at the layer call date 31/12/2017. To go to the reserving sublayer, you can press the button Confirm Layer Selection again. For now, let's focus on the realistic layer. In case you accidentally selected the reserving layer, you can still move around between the elements shown in the current location box. Or alternatively, you can restart the selection again by clicking on the Model Name drop-down and then confirming the layer selection as required. Select the appropriate program name, step date, and record identifier. Observe that the first element in the step date drop-down list is the portfolio date or time step 0, and the second element is the first projection step or time step 1. Note that if the portfolio date is selected, the non-portfolio variables will not be available in the variable name drop-down list. to see the value for non-portfolio variables, such as cash flow-related variables, in the variable name drop-down list, move to the first projection step. Additionally, to select an event in the Step Event Loop drop-down list, you must be in a projection step where at least one event is calculated. By using the analyzer, you would be able to check the dependencies between variables and steps or events. In the results grid, analyzed values are indicated by a yellow outline around their cells. For instance, analyze the variable expense renewal. At 3103/2018, we can see that it uses values from the precedence variable list from both current and previous projection steps. Analyze the variable CF premium event. We can see the calculation refers to values from the current event and the previous projection step. If you want to analyze a specific value in the grid, then go to the cell and either select and press Enter or right-click and select Analyze. Simple line graphs of calculated values are also available in the Graph pane by ticking the box to the left of each variable in the results grid. A graph can be useful for quickly checking that the pattern of values is as expected. To view arrays or life tables, click on the cell itself within the results grid for the whole table to display. You can also choose to hide or show events from the ribbon, depending on whether they take up too much space in the results grid. Finally, you can navigate between previously analyzed values using the arrows in the ribbon and move between variables by clicking the variable boxes in the diagram view. Appendix 3. Compare tab. We now have two product modules. Let's assume we want to see how the product modules differ. For instance, the term assurance product has fewer benefits, as we would not expect it to have surrender or maturity benefits. In the ribbon, select View and then Compare tab. From the Workspace Explorer, select the module Endowment NP. Right-click and select Add to Left Compare. Now select the module Term Assurance. Right-click and select Add to Right Compare. You can unpin the Workspace Explorer, the Properties panel, and the Chooser so the central window shows in the full screen. In the Compare tab, a yellow highlight indicates there are differences between the two components. The blue color indicates something is present in one of the items being compared, but not in the other. In the General tab, observe that it shows the two extra submodules in the Endowment module, which are not present in the Term Assurance module. Go to the Step tab and see that nothing is highlighted in yellow. So the code in the two modules is identical, apart from the Endowment module having two additional submodules with extra variables. In the ribbon, go to Window and click on Close All Components, so the modules shown in the Compare tab are closed. Now we will create an example of different values to demonstrate how they are highlighted in the Compare tab. At the same time, we will cover how to embed new code, which will be helpful when using standard code. One of the possibilities to perform a sensitivity with a new interest rate is to override a variable in a new component. Add a new assumption set with the name realistic_assumptions_sense_int. Drag in realistic assumptions as a sub-assumption set. In the Variables tab, copy the whole row for the variable int rate and paste it into the empty row at the bottom of the grid. The column Assumption set in the grid shows that int rate is now a standalone variable in assumption set realistic assumptions sense int. This action overrides the variable int rate in the assumption set realistic assumptions. For instance, if you delete the variable int rate in the main assumption set, the definition of the variable in the subcomponent will show up again as it hasn't been deleted there, just suppressed. Make sure you undo this change. Modify its value from 5% to 4%. From the Workspace Explorer, add each assumption set to the windows in the Compare tab. In the General tab, the new assumption set shows the subcomponent in blue, highlighting it has an extra subcomponent. In the Variables tab, the variable int rate is highlighted in yellow, with the properties, formula, and assumption set showing the differences. Note the red circle in the formula pane on row 1 of both sides. If instead we had compared a variable with a long formula, say with several if conditions, then the red circle would be alongside all the rows that differ, drawing attention to the specific differences in the formula. Also, it is possible to copy code from one component in the Compare tab to the other component on the other side. Go to Window and click on Close All Components. Now observe the options which are available in the Compare tab within the ribbon. For example, if the option Ignore Spaces is selected, will mean that the comparison will ignore differences that are due to additional spaces or line breaks present in one component but not the other. The Compare tab can be used to generate a multi-way report to identify differences between workspaces. For example, you can drag a collection of components, such as all assumption sets, from one workspace onto one side of the Compare tab, and the corresponding collection from another version of the same workspace onto the other side. A whole workspace can be compared, but you need to select all components rather than the workspace title. Select Multi-Way Report, and then a location on the C drive to store the report as a .txt file. Once the comparison is done, then the report automatically opens in Notepad. It can be useful to generate a report to ensure all differences are captured. For instance, differences in formulae on the Event tab may be missed if event variables are not reviewed. Appendix 4. Recalculation Steps. Open the Reserving layer and go to the Properties tab. Look at the Recalculation Steps property. This property applies to a sublayer and defines, via an expression, when Modeler should recalculate the sublayer instead of using results from a previous calculation when a calling layer references a value from it. This can be a date expression as shown. This expression specifies a sequence of dates, starting from the layer start date of the calling layer and ending with its layer end date. It is only at the step end dates that the calling layer can call the sublayer, so Modeler recalculates the sublayer on the step end dates in the calling layer on or after the dates specified in this property. Alternatively, you can set the property to once to calculate the sublayer only at the layer start date for the calling layer. This is the default value of this property, or set the property to all, or make it blank to recalculate the sublayer at every step end date of the calling layer. The difference between these options is shown in these slides. First, we observe the case where the reserving sublayer is calculated just once. In the second animation, we see how the reserving sublayer is recalculated monthly up to one point in time, and yearly thereafter. It is important to note that such a run could take a significant time to execute, especially if running monthly in the calling layer. Instead, it is possible to limit the number of projection steps for which the sublayer is called from the main layer, either setting the recalculation steps property to once or defining a suitable date expression. Note that for the steps at which the sublayer is not run, the value of the variable is taken from the latest sublayer recalculations. It is worth considering how the variable in the sublayer is calculated, as it may be that the value is exactly right, since it will be the per-policy value. In this case, it may be that you only need to kick off the sublayer once. However, it may be that the results are slightly inaccurate. For example, if expenses are included in the reserve, and the expense assumptions, such as the inflation rate, are different between the realistic and reserving layers. This will result in applying reserving inflation for the steps where the reserving projections is not invoked, rather than realistic inflation. The inaccuracy will normally be small and produce a second-order approximation in the overall results, which are likely to be worth living with to significantly speed up the runs. If necessary, you can often feed up additional values to the calling layer and ratio them to improve the accuracy. Appendix 5. Optimizing run speeds. Considering how often the sublayer is invoked, it can significantly increase run speeds. It is therefore one of the primary factors to consider when trying to reduce the execution time of a run. We will now look at some other aspects affecting run speeds. For example, 1. Multi-threading enables machines with multiple processor cores to process multiple records of the same model simultaneously. Therefore, if you have modeler using machines with more cores, this can significantly reduce runtimes. 2. Modeler only compiles the necessary code to calculate the variables in an output report for live and filtered sample runs. Runtime will not be spent unnecessarily calculating irrelevant code. It also means that incorrect code that is not required to generate the output will not cause generator or runtime errors. 3. Modeler can process record by record or step by step. If the model needs to carry out dynamic decisions depending on the results calculated at each step, like in an ALM calculation process, then modeler will automatically process calculations step by step. Depending on the model and the number of records to be processed, one method of processing will be faster than the other. For example, if you have an extremely large data file and the model is running step by step, then, since lots of memory is required to store the results for the records at each step, step-by-step processing is likely to be slower than record by record. Conversely, if the model has sublayers, then it may be slower to run record by record as the sublayer is invoked for every record rather than once for all the records at a given point in the calling layer. The default is for Modeler to run record by record, if possible. But for a run that can run record by record, it is worth processing both ways and comparing the run speeds. However, the following conditions force Modeler to run step by step. You can force a run to execute step by setting the force step-by-step property to yes. Modeler automatically processes any projection layer of a stochastic model using step-by-step processing. Global calculations, where values are fed back into a child program from a parent program. A parent program, in the projection process used by the layer, contains a calculation grouping. Use of system variables like earliest record start date or latest record end date, or at least one sublayer of the layer is processed step by step, and therefore satisfies at least one of the above. Users should check that they are not inadvertently forcing Modeler to run step by step, which may slow things down. This can be confirmed in the generator information from the run summary in any results workspace. Other factors to consider for optimizing runtimes are number of records processed. You may consider using model points, particularly for stochastic runs. Number of projection steps. Could they cut off the run earlier if results from later years don't affect results materially, or lengthen the projection step and use of events? Number and size of arrays. Machine memory, particularly if running many records step by step. Amount of code being processed. Users need to consider if all the code in a model is needed. Split one model into smaller models, perhaps running part of the data file in each model, and you can use a batch to distribute the models. Consider cutting down the number of scenarios. Perhaps very little is added to the accuracy of the model by using 10,000 scenarios compared with 5,000 scenarios. Use distributed processing to process scenarios over as many machines as possible. Appendix 6.0, Miscellaneous Topics, Part 1. Individual output reports. Individual reports, output, individual values for the variables specified in the output report attached to the program for all the records processed. Values may be output pre or post the application of any record multiplier. Individual reports are particularly helpful for checking results, like reserves or present values. Users need to specify the date at which you require to view the variable. For example, variable portfolio date, a date expression, or a hard-coded date value. In case the dates property is left blank, values at the portfolio date will be included in the individual results. If the same variable is required at more than one date, then users need to include the variable multiple times in the output report, but with different output aliases. If the output report includes the system variables record identifier or group identifier, R3S Modeler sorts individual results by these output report variables when you tick the Sort Individual Output checkbox in the Select Output to Display dialog box of the R3S add-in for Microsoft Excel. Finally, Note that the multiplier property is only relevant for individual output. Aggregated output is always post-multiplier. Now look at the individual report example included in the delegate binder in section 6 on page 22. Try replicating this example in your workspace and add the output report to the individual report property of each child liability program in the realistic layer before viewing the solution in the next video. Also, make sure you run your model on live mode and check individual model results. Appendix 6.1, Miscellaneous Topics, Part 2. The completed Individua report component is now shown on the screen. You should have the following variables in your output report with the relevant properties. Now, pause the video to double-check your entries. Indicator variables. Indicator variables are used to store numeric expressions and are calculated as integers. They have an additional indicator values property that may be used to define labels, which can be applied to represent numeric values in formulas. For example, gender information is usually stored as an indicator variable. For example, 0 for males and 1 for females. It is much easier if we can refer to character values like male or female in the code rather than integer values. Add the variable sex_code and set the data type to indicator. Set the indicator values property to male equals 0, semicolon, female equals 1. This means that in the formulae, instead of using if sex code equals 0, we can instead refer to if sex code equals male. Note that indicator values are case-sensitive. Process record numbers. You can select the data records processed by a data source or program by specifying their sequence numbers in this property, using a combination of range and set function calls. For example, the expression range 4, 20, 8, semicolon, set 30, 40 would select only record numbers 4, 12, 20, and then 30 and 40 for processing. The range applies after any filters. That means the sequence numbers apply to the sequence of records remaining after modeler has first skipped any records in a data file or applied any filter formula. Orphan variables. Variables that exist in a workspace but are not contained within any component of that workspace are known as orphan variables. They may arise during model development, for example, when you change your model and delete a variable from a program, or you misspell a variable name and then retype the correct variable name rather than changing the name in the list of variables in the chooser. You can use the Orphan Variables dialog box to view and easily delete the orphan variables in a workspace. Go to Tools, Orphan Variables. This identifies and lists all the orphan variables in a workspace. Users have the option to select all variables, clear all variables, and delete all the selected orphan variables from the workspace. Within the Orphan Variables dialog box, variables can also be protected or unprotected by right-clicking them and selecting Protect Unprotect Variable. Appendix 7, External Assumptions Part 1. The company model performs calculations using assumptions which are defined internally. Now we will adjust so that the assumptions are read externally from an Excel file. Modeler can read assumptions from external sources. Assumption set variables within an assumption set can be set up to receive values from an external source. It does this by connecting to databases that contain the values of the assumption set variables at runtime. For example, Modeler can read assumptions from Microsoft Excel workbooks, Access or SQL databases. Advantages of using external assumptions are that you can use existing spreadsheets or databases that contain assumptions as inputs to Modeler, avoiding the need to input or import assumption values from those spreadsheets into the assumption sets. This can be especially useful for large arrays. You can update assumptions in a spreadsheet more quickly and easily than assumptions in an assumption set. You can use them for creating separate files to run sensitivities. Open the help file and look for the topic Using Microsoft Excel as an external assumption source. Look at the following examples. For a scalar, we can define a value in any cell and give the cell and the cell above a range name like this. For a one-dimensional array, we can put the indices in a column with the data values in the next column and again specify the two columns, including the row above, as a range name. For arrays with more than one dimension, the first dimension needs to be set up as columns, and the second and subsequent dimensions, with a maximum of 5, as different rows, as shown in these examples. In the next videos, we will show how to set up assumption set variables to read from an external Excel file. Appendix 7, External Assumptions, Part 2. Now, let's set up a couple of assumption set variables so the values are read from an external Excel file. Add a new assumption set called Realistic Assumptions EXT. Drag in the assumption set Realistic Assumptions as a subcomponent. Go to the Variables tab and override variables int rate and surrender rates so that we have copies of both variables belonging to the assumption set Realistic Assumptions EXT. Now let's set up these two assumptions in Excel. Open a new Excel spreadsheet and save it in a new folder alongside your workspace called Assumptions. Give it the name external_assumptions. In cell B3, write the variable name int rate. In cell B6, type the value 5%. Set up the range name int rate in cells B5, B6. The range names given in Excel do not need to correspond to the names of the corresponding variables within Modeler. Although this is a convention which you may wish to adopt. You can also highlight the range name in a different color, just for clarity. Save and close the spreadsheet and go back to Modeler. Go to the Assumptions set, Realistic Assumptions EXT in the General tab. Right-click on the property Assumption Connection String and select Locate OLEDB Connection String. Make sure the default OLEDB is selected in the Assumption Connection Type property above. Select Microsoft OLEDB Provider for ODBC drivers in the Data Link Properties window. Click on the Next button. Select Use Connection String and click on the Build button. In the Select Data Source window, go to the tab Machine Data Source and select Data Source Name, Excel Files. Click OK and browse through the directories to select the file external_assumptions.xls. Click OK and press the Test Connection button. If the test connection is successful, click OK again, and the connection string will be created. Note that the file connected to here is not the actual one used by the model. We shall see later that the file used is the one specified in the model, layer or program. This connection in the assumption set works like a template and enables us to set up the assumption table and specify external assumptions. At runtime, Modeler uses the assumption connection string properties of a model and its subcomponents, and ignores the assumption connection string property of each of its assumption sets unless you use the assumption file property. In the Variables tab, select the property, Assumption Table of the variable int rate. Go to the Formula pane, right-click, and select Locate Table to select the table int rate. Note that the connection string also needs to be specified in any sub-assumption sets that use external assumptions. Otherwise, you may receive an error if the connection string is missing in the subcomponent. Select the Formula property. Go to the Formula pane, right-click and select Specify External Assumptions. This is a scalar, so we just need to tick the scalar tick box. Now press the Check button. Modeler tells us that the scalar value is 0.05. In the next video, we will show how to set up an array variable read from an external data source. Appendix 7, External Assumptions Part 3. Now let's set up the array variable surrender rates so it reads from an external data source. Go back to the file External Assumptions. In cell B9, define the table name surrender rates. In cells B11 to D15, enter the array data, which is currently defined internally. Define the range as surrender_rates. Save and close the spreadsheet. Go back to the assumption set, Realistic Assumptions ext. In the Variables tab, select the Assumption Table property of the variable surrender rates. Go to the Formula pane, right-click and select Locate Table to select the table Surrender Rates. Select the Formula property. Go to the Formula pane, right-click and select Specify External Assumptions. When specifying an array, we need to define the dimension name, the start position, and the data type for each dimension. Set them as follows. Dimension number 1, product. Start position 1. Data type, character. Dimension number 2, duration in force. Start position 1. Data type, numeric. Click on the check button to test the array is being read correctly from the spreadsheet. Notice how the indices for both the product and duration in force dimensions are brought in from the spreadsheet. Next, we need to specify how the model should locate the external file required for execution. We do this in the property External Assumptions Connection String, which may be specified at the various levels in the model. The levels at which the assumption sets may be specified are the following. Model for a whole model. Data process for all data sources. Data source for individual data sources. Layer for all programs in the layer. Program for individual programs in the layer. In our model, we will define the External Assumptions Connection String property within the realistic layer. Open the runtime settings within the realistic layer, then select the layer name to display its properties. Right-click in the External Assumptions Connection String property of the layer and select Locate OLI DB Connection String to select our Excel assumption file as we did previously. Change the assumption set for the realistic programs to use the new assumption set, Realistic Assumptions EXT. Finally, run the model using filtered sample mode and confirm there are no errors.